Welcome, everybody. It is my pleasure to introduce our speaker for the Warren Lecture Series. Our speaker is Dr. Charles Schwartz, who is a professor and also chair of Civil and Environmental Engineering at the University of Maryland in College Park. Dr. Schwartz has all his degrees from MIT, and he is part of the very prestigious pavement program that is known worldwide and brought immense contribution to the area of pavement engineering. His teaching and research activities encompass pavement design and analysis, advanced soil mechanics, computational geomechanics, pavement mechanics, and material characterization and constitutive modeling. He played leadership roles in many national research projects, and he assists on a regular basis federal, state, and local agencies and private firms on pavement-related topics. He is a member of Transportation Research Board. Actually, he's a chair of AFD-80, Pavement Structural Modeling and Evaluation Committee, also chair of the Geo Institute Pavement Committee in ASCE, and member of AAPT and ISAP. Also serves as an editorial board, a member of the International Journal of Pavement Engineering and Transportation Geotechnics. He also co-developed and led and was a lead instructor on the NHI, National Highway Institute course, Geotechnical Aspects of Pavements. Let's welcome Professor Charles Schwartz.
Thank you, everybody. It's a pleasure to be here. It's almost like going home. I grew up in Wisconsin, and so I like to get back to the Midwest as often as I can. Before I get into the substance of my technical talk, I've learned an awful lot about the University of Minnesota over the last day, and so I thought I'd take the opportunity to tell you a little bit about the University of Maryland College Park. Actually, I knew quite a bit about the University of Minnesota before I got here yesterday. I've been at the University of Maryland at College Park for several decades now. It's located in the Washington, D.C. metropolitan area. It's actually quite well located, about midway between Baltimore and downtown, so we get to draw upon two diverse, distinctly different metropolitan areas. But the location also is great for us because it puts us right in the middle of a lot of the funding agencies and the policymakers, and we've got access to outstanding research facilities and some of my own work. In fact, some of the work I'm going to be talking about here today, we actually did it out at Federal Highways Research Facility out at the Turner Fairbanks Highway Research Center. And a lot of major media outlets for getting the word out about what we're doing. Just to give you an idea of how large our program is, we run about 450 undergraduates, typically, enrollment, and a couple of hundred graduate students. You can see the numbers here. So, something on the order of 120 to 140 bachelor's degrees each year. And again, you can see the numbers for master's and PhD degrees. So it's a medium-sized program. We've got 27 and a half tenure and tenure track faculty. One of our faculty is a joint appointment with fire protection engineering. We have one of the, I think, only two accredited fire protection engineering programs in the country. And again, some full-time lecturers and adjuncts, and some searches going on right now for some new junior faculty. We do a fair amount of research. This number bounces around from year to year, but in 2015 we were 8th among civil engineering programs in terms of research volume, 25th overall in rankings, 19th among publics. And we offer the full range of technical subspecialties in civil engineering. In fact, we kind of pride ourselves for our undergraduate program in particular by giving our students a very broad exposure to all aspects of civil engineering. Let me talk about a couple of initiatives that are going on before I, again, go back to my talk. I've been impressed by the laboratory facilities here. You've got to have at least 5 times more square footage in labs than I've got under my control. And the space that I had under my control was in terrible shape, literally had been neglected for decades. And so when I came in, I said, all right, we're going to have to do something about it. So we raised some money. And just this last August, we finally broke ground or started demolishing the old lab facilities. And so these are our main teaching labs for soils and structures and materials. And the problem was not only were they old and deteriorated, but they were becoming a choke point in our program in that we have roughly 200 students that have to go through there every year, and we couldn't run that many through. It was becoming an impediment to graduation, and so we had to do something about it. Plus, we were looking at accreditation this year, and I thought, what could be better than to tear up our labs just before the accreditation visitors come? So anyway, so we demolished everything, and it's going to look great when it's done. This simply shows that architects have absolutely no idea what goes on inside of a materials and soils laboratory. But it's actually going to be fairly dramatic space with curved glass walls and all sorts of neat stuff. It'll be named after, we're lucky in that we have two of the top 10 construction companies in the Baltimore and Washington area. And the one in Baltimore is Whiting Turner Contracting, and so they provided the leadership pledge for this. And so they get naming rights for the laboratory. So this should come online for classes again in the fall of 18. Another big recent development is literally for decades we had been trying to get a Maryland Transportation Institute, a multidisciplinary center that would unify all of the transportation research going on campus, a lot of which goes on in the civil engineering department. And this is a very busy slide, but it sort of gives you an idea of the strength of our program that sort of motivated us to do this. Nobody ranks transportation programs separately, but if you look at things like journal publications and funding and so on, we end up very well. We actually have two big transportation components at Maryland. One is our regular tenure and tenure track, the research faculty, which are very active. And then we have a separate Center for Advanced Transportation Technology, which doesn't do so much in terms of basic research, but provides advanced operational support for the region and for the country. Among other things, they manage the entire I-95 corridor from Florida up to Maine. And part of the Center for Advanced Transportation Technology is what's called the CAT Laboratory, which basically collects and archives transportation data. And today they are collecting and archiving 8 billion records of transportation data every single day. And they've done great stuff in terms of data visualization tools for looking at this data. All kinds of people, Google comes to us asking for our data. So it's a huge resource, and that's one of the things we want to take advantage of, capitalize on in this Maryland Transportation Institute. But again, you can see some of the areas that we want to get prominence in. This is exciting. As I said, this has been a couple decades in the making, and everything sort of came together, the stars aligned, and we were able to get some base funding in place for this, and it's going to be launched this fall. Another big initiative for us, and this is in part geographically driven, is disaster resilience. You may remember Superstorm Sandy that went up the East Coast a few years ago. This is what Atlantic City looked like after Sandy went through. Well, if you look at Maryland, which is on the Chesapeake Bay, largest estuary in North America, in the Northern Hemisphere, and you look at Baltimore, this is the Inner Harbor sort of tourist area in Baltimore. We've got Annapolis, which is on the Chesapeake Bay. We've got a lot of ocean frontage in Maryland. Maryland has as much tidal coastline as all of California, which is a problem because we have sea level rise. We have a geologic anomaly in the mid-Atlantic where we're actually seeing regional subsidence. So we have sea level rising, the land subsiding. And if you look at projections, this is the effect of projected sea level rise by the end of the century on the Chesapeake Bay. Here's the Chesapeake Bay, here's Washington, Baltimore, Annapolis. And you can see that already, just from sea level rise by the end of the century, a lot of the eastern shore of the Chesapeake Bay is going to be subject to regular flooding. Now, if you put a storm surge on top of that, if something like Superstorm Sandy came up the Chesapeake Bay and put a 15-foot storm surge on that, you're looking at this. We basically flood 40% of the eastern shore of Maryland. We have major flooding in these major metropolitan areas, Annapolis, Baltimore, and Washington, D.C., with incredible consequences. And so we have established the Center for Disaster Resilience to be sort of a regional resource for people trying to grapple with these future trends. Another thing I just wanted to point out, I expect Joe does the same thing here. Our faculty are very good at getting their work out before their professional colleagues. What we in engineering tend to be not so great at is getting it out before the general public to let them know what we do. And so this has been a priority for us, and we actually have been quite successful in recent years. Both in terms of the number of media hits and where they were placed. In fact, we have an article in the current issue of Rolling Stone. We've become rock stars. Current issue of Rolling Stone on our group that looks at flood risk and flood resiliency. But you can see where things have been published. This is really valuable. As I said to my faculty when I took over as department chair, I said, look, when I'm driving in the morning and NPR is doing a soundbite on an engineering problem, I want it to be our people giving the soundbite, not Virginia Tech. And so we've been making some success on that. And then the last thing I wanted to point out, this just happened 2 days ago. The university received by far the largest donation in its history. And it turns out it's the 6th largest donation to a public university ever. The A. James and Alice B. Clark Foundation from Clark Construction, who are also the benefactors of our engineering college, which is the Clark School of Engineering, donated almost $220 million to the university, which is going to be used for a number of undergraduate scholarship programs, several categories of graduate fellowship programs, 2 different sets of endowed chairs, and major facilities improvements. 2 buildings, basically, what should come out of this thing, one of which will be the new home for civil and environmental engineering. So this is a big deal. We're really excited about this. Anyway, so that's a little bit about Maryland. Let's go back to the technical part of this, standardizing lightweight deflectometer modulus measurements for compaction quality assurance. This is actually the results from a transportation pooled funds study that I led that finished up about a year ago. Is there anybody from MnDOT here? No, let's see. I mean, I feel like I'm preaching to the choir here because MnDOT has been using non-nuclear or deflection-based quality control for compaction forever. You know, they decided from the very start they didn't want to get into the nuclear gauge business and have gone a different route. And so we're following along. It's a pooled fund study. You can see the states here that were involved. Minnesota and Indiana are green because they were not formal members of the pooled fund study, but since they had been doing so much work in this area, they became sort of informal members of the pooled fund study and participated in all of the technical advisory committee discussions and so on. John Siekmeyer from MnDOT here was extremely instrumental in setting up this pooled fund study and in helping us to make it a success. But what's the objective? Okay, we're looking at compaction control. Any geotech students here? How do most places do compaction quality control? For, you know, you're going out and you're compacting an embankment. How do you determine whether it's compacted enough?
Sand coal?
Sand coal.
Well, I'm going to be 60.
We use nuclear density gauges, right? We take a nuclear tip probe and put it in the ground, and the attenuation of the radioactivity gives us an indirect measurement of density and moisture content. Okay, and we do that for pavement engineering. Okay, and so the question is this: what are the inputs for our pavement design procedures? Is density an input for our pavement design procedures? No. Is it an input for embankment design? No. What are the inputs? Are there things like stiffness and strength? Okay, and so the question is, well, why don't I measure stiffness and strength? And the answer is, it's a lot harder to measure those in situ. It's easier to measure density using a nuclear density gauge. The analogy I always use on this is it's like the old joke about the drunk looking for his keys under a lamppost. That's what nuclear density gauges are. That the policeman comes along and says, hey, buddy, can I help you? You know, you're looking for your keys. Is this where you lost them? And the drunk says, well, no, actually, I lost them half a block away, but the light is better here. You know, and we sort of use nuclear gauges because they shine a better light than other techniques. So anyway, so the objective of the project was to come up with a straightforward procedure, and the emphasis here is on straightforward procedure for modulus or stiffness-based compaction quality control and quality assurance using lightweight deflectometers. And the key thing here is it had to be suitable for practical implementation by field inspection personnel. We wanted something simple. People have been using lightweight deflectometers for a long time in a research mode, but they had never, except for places like Minnesota and Indiana, they had never really quite made it to practical acceptance. And so we had a whole bunch of tasks, the standard kind of research tasks you would have in a project. But to cut to the chase, to give you an idea of where we're going, we basically we're looking at coming up with two specifications at the end of this. Specifications in AASHTO format that could be the basis for a real field inspection program based using these devices. And so the first one is a draft specification for how you do this in the field. How you go out and apply, use an LWD in the field, a lightweight deflectometer. And again, a lightweight deflectometer is nothing more than a drop weight with a sensor that measures deflections. Okay, so it's like the big falling weight deflectometers that are used commonly in pavements, only at a much smaller scale. So it's a load and deflection measuring device. Sort of a dynamic plate load test. It's another way to think of it. So we wanted to come up with a draft specification for field compaction control using stiffness instead of density. And a lot of this looks kind of familiar. We want to test within a couple hours of placement. That would be the same if I were doing density-based QC testing. We want to keep the field moisture content within the optimum by a certain amount. Okay, that we're used to doing that. That doesn't change. The thing that does change, instead of looking at a percent compaction in terms of density, we're now looking at a ratio of the modulus that we measure in the field versus a target modulus that we've determined for that material in the laboratory. So that has to be greater than some threshold value, where that target modulus is going to be soil specific and also structure specific. If you're looking at pavements where you have a layered system, the depth of influence of these devices usually extends beyond one layer, and so we've got to correct for structural effects. So that was the first specification. And the second one is for how we go about determining this target modulus value for the material. And I'll talk about that more, but basically the approach we finally settled on was a very simple one. We're still going to do Proctor compaction testing to measure the density moisture curve, but at each stage in the Proctor test, what we're going to do is take our lightweight deflectometers and do testing directly on the mold and measure that stiffness in the laboratory in the mold at that particular density and moisture content. And we're going to do this at multiple moisture content values in the same way that we measure density at multiple moisture content values. And then we're going to do it at different drop heights so that we can get the stiffness at different stress levels, since for most materials the stiffness is stress dependent. So the major issues that we had to confront are basically the same major issues that everybody who's worked with lightweight deflectometers has had to deal with. That there are a bunch of manufacturers of these devices. They have different operating characteristics in the way that they measure load or don't measure load, in the way they measure deflections. And the consequence of that is that if I have the same soil and I have 3 different devices, I'm going to get 3 different measurements of modulus, which is problematic. We have to worry about moisture influences, because that's going to have a big effect on stiffness. If we don't have moisture control, and if I were a crafty contractor and I knew that you were going to be controlling or checking my compaction based on stiffness, what would I do? Well, I'd compact dry of optimum, because it's easy to get a stiff material when you compact it dry of optimum, but that's not the material I want. So you need to have some moisture control on this. Initially we thought we'd have to worry about drying effects, between the moisture content at the time of compaction and the moisture content at the time that you actually did the test. But in the end, we said, well, no, look, if this is going to be a quality control test, you've got to do it quickly. You're going to have to do it within 2 hours of placement, and you don't get much drying going on in that short of a time period. Stress level I mentioned. Finite layer thickness. If it's a pavement system and I'm doing this on top of an 8-inch granular base layer, well, I have to factor in the stiffness influence from the underlying subgrade in my measurements. And then the key thing was practicality. We wanted this to be a laboratory test that didn't impose too much additional cost and burden on the technicians in the laboratory, and also which would be easy to do in the field. And again, I mentioned traditionally we've used density-based compaction, quality control and quality assurance specifications, and it's an indirect measure of the quality of the material, and it measures a property that we're not really interested in, so that's problematic. It also doesn't work on all materials. A lot of agencies, highway agencies now, are looking at recycled materials, cold-in-place recycled materials. And the interesting things about these is that the stiffness actually increases with time as the material cures in the field. Well, that's problematic for density-based quality control and quality assurance, because the density doesn't change at all. So I can't see how the properties are improving over time because the density stays the same. Whereas if I'm measuring the stiffness, I can actually see the stiffness increase over time. There are some states that have looked at this. Again, Minnesota and Indiana being at the lead, but Florida's dabbled with a little bit, Nebraska. It's been used more in Europe. There have been some previous NCHRP projects looking at parts of this. The other thing that this touched on was resilient modulus testing in the laboratory, triaxial testing, cyclic triaxial testing. Most agencies have not really been willing to implement this. They view it as too expensive and too complicated. And for this purpose, you actually have the problem that you don't know what the moisture content is going to be in the field, and you really want to test the material at the same moisture content. And so you could, in the laboratory, go and do resilient modulus testing over a whole range of moisture contents, but that would really be complicated and expensive and time-consuming. So we wanted to steer away from that. And we wanted to come up with a scheme that gave us a smooth transition from our density-based methods that everybody is familiar with that applies to a range of geomaterials, including things like cold in-place recycled materials, full depth reclamation, for example. We wanted to have consistency among testing, design, and construction. If design is based on stiffness, then we want to have our testing based on stiffness and our construction control based on stiffness also. Cost efficient. Again, if we're doing it for quality control, it's got to be done right after placement. Doing quality control testing 2 days later after placement doesn't help the contractor maintain quality. You've got to do it right away, right at the same time. And most importantly, we wanted to have an easily determined way, or easy way of determining the target modulus values. And so again, the innovation here was to do small-scale lightweight deflectometers using a 100 millimeter diameter plate or 150 millimeter diameter plate, depending on the size of the mold, directly on the proctor molds to get the target stiffness value that we're looking for. So what we did is we looked at a variety of equipment. As I said, there's a bunch of manufacturers of these lightweight deflectometers, and they have different load measuring devices and different buffers and different displacement sensors. And we sort of looked at the range of material and chose 3 different manufacturers that sort of covered the whole spectrum of options available. The Zorn, which is used here in Minnesota primarily, which measures deflections, accelerations directly on the top of the plate. But it's unusual in that it doesn't have a load cell, and so it can't measure the peak load during the drop. You have to calibrate it and assume that calibrated peak load is the same for all conditions you're testing. There's a Dynatest LWD that does have a load cell and uses velocity sensors instead of accelerometers to get at deflections. And then a new one by Olson Engineering that has both a load cell and accelerometer. So it sort of covers the whole spectrum of options that are available. The other thing you have to have is some way of quickly determining moisture content in the field. That is one of the good things from the nuclear gauges, that they give you a direct moisture content. And if you're giving that up, you've got to find something else to replace it. And we looked at a couple of devices, but the one we really settled on, and the one that we really like, is this Ohaus moisture analyzer, where you put a little sample of material in this container, in this little cup. You close the lid. The lid has halogen lamps in it. So the halogen lamps come on, they heat up the specimen. It's got onboard continuous measurements of weight that gets displayed on the screen. And so you draw out the sample. You could do it in the field. You just need a little generator in the field to run this thing. And in 20 minutes, you can get a field moisture content. And it works for basically all kinds of materials. And Ohaus, when we first started this, they only had a small version of this, which didn't work that well for aggregate bases, for coarser material, but now they offer several sizes of these devices. And it's really a good device. And what you're seeing here is simply what the moisture content that you measure using the Ohaus moisture analyzer versus, in this case, water content from a nuclear gauge, could be water content from oven drying, but you get good agreement, good correlation between the two. So it's an accurate device also. We did a bunch of tests, some of them more for validating techniques, approaches and others for verifying things in the field. So as I said, we went out to Federal Highways Research Center out in McLean, Virginia, the Turner Fairbanks Highway Research Center, where we were going to do some large box tests in the laboratory. And the people at Turner Fairbanks said, well, you know, we have these pits that we dug, in concrete lined pits that we dug a long time ago for some research that never came about, and they just have been sitting there for a decade, empty. Why don't you use these? We said, that's fantastic. So we went out there, and these were about 15 by 15 foot in plan, deep pits that we could construct using, you know, carefully controlled construction techniques, carefully controlled materials, and went in and basically did a full suite of tests. You know, gradation, classification tests, resilient modulus tests, laboratory resilient modulus tests, ran all the compaction tests, and then also ran all of our LWDs, all three types of LWDs. They actually had a static plate loading frame on these pits, so we could do static plate loading tests. We did nuclear gauges. We borrowed from MnDOT a device they call their beam verification tester, so we could, in conjunction with this, also test the devices themselves, the individual LWD devices. So we did a lot of testing out there, essentially to sort of refine our approach and to collect some preliminary data that we could use to look at to make sure that we were on the right track. And so that worked out very well. That took basically a whole summer to construct those pits and collect all of the data. This just shows some of the results. These are showing, these are just gradation curves here, but this is showing the modulus measured using a lightweight deflectometer, different types, Zorn, Dynatest, Olson, versus the modulus from a static plate load test. And again, not perfect agreement, but generally pretty good, you know, alignment along the line of equality. It's only when we got to sort of stiffer materials we started to see a little bit of deviation. So that's just an example. Here's an example of, or here's a picture of the static plate loading test. They had this loading beam on rails along the edge of the pit. Here you can see the pit laid out with all of the testing locations. And then we would go in and do the static plate loading test.
Sorry,
yes?
Could you clarify on those plots, what do you mean linear versus the particular, what are the different?
Oh, okay, so the red line is the line of equality. The linear.
What that means, what is the line of equality?
I'm sorry? The line of equality? Yeah, where the vertical equals the horizontal.
Oh.
Okay. And this is just the linear regression line through the actual data points.
And the predicted is based on?
Is the measure, predicted is the wrong term. It should be measured using the various lightweight deflectometer devices.
And so in the horizontal?
The horizontal is what we measured from the static plate loading test. And the vertical is what we measured from the lightweight deflectometers over here.
Okay, thank you.
Okay.
And are they all the typical, I noticed there's 3 curves on what looks like a grain size distribution.
Yeah, I should have apologized from the start. This is the problem of web meetings. These slides were prepared for a web meeting where everybody's sitting there looking at them from this far away, and they don't project very well. I apologize for that. This is just a gradation curve, percent passing versus sieve size.
But there's 3 different.
It's 3 different materials, I'm sorry. So there,
okay.
This is a coarse granular base material,
Uh-huh.
and then these are 2 subgrades. The natural subgrade at the accelerated loading facility out at Turner Fairbanks, which is a silty soil. And then we brought in a high plastic, we imported a highly plastic clay as a different kind of subgrade.
Okay, and then the curves at the bottom of the slide are for which grain size distribution or which system?
Let's see, which one is this? It doesn't say. I'm guessing it's the ALF subgrade. Yeah. Any other questions? Feel free to holler out. So we looked at we visited a bunch of field projects. Okay, so after we did those big pits, we said, all right, we're going to go and take this on the road. So we went and we tried to do testing in the states of all of our participating agencies, and this just sort of lists where we went and the kinds of soils we tested. It turned out that a lot of these sites didn't work out for verification purposes, in that when we would get there, we found out that they had placed the material 3 days ago, and so it violated our window for the specification. If you're testing a granular base layer, what you want to do is to be able to go in and test the subgrade before you place the granular base, so you know the stiffness of the layer that you're putting the material on. And sometimes we got out there and found they already covered the subgrade. And so, you know, we visited a lot of sites, we learned a lot, but when we were all done, there were only about 5 or 6 of these that actually gave us the data we were looking for. But at each one of the sites, we would record weather data. We would lay out a testing plan, sort of a grid. And in each grid, we would do the 3 lightweight deflectometers and a nuclear density gauge. We collect samples for field moisture content measurement. We collect samples to take back to the laboratory for laboratory testing. But again, the methodology that we developed and refined through this field verification process, again, is in the laboratory using the Proctor mold and a small diameter plate to do lightweight deflectometer drops directly on the mold. And what that allowed us to do is to not only develop a density versus moisture content curve, the standard Proctor compaction curve here, but also a stiffness versus moisture content curve shown here in the green. And we would do that for different drop heights, and so we would actually get a family of these curves depending on different drop heights, and we'd fit a regression to that to allow us to calculate modulus as a function of moisture content and stress level or drop height. And then the next step is to go out and measure the stiffness in the field and to measure the moisture content in the field. And then our compaction criteria were that the ratio of the stiffness in the field to the target had to be greater than some threshold, and the moisture content at compaction had to be within optimum plus or minus whatever the tolerance was for the specification. So again, a very simple specification, a very simple approach that builds directly on the way we are used to doing things, doesn't introduce a whole lot of new wrinkles. And again, the reason for that is to try to make this implementable. We wanted it actually to get used in the field. Again, just a little bit on the background. So the LWD drops on the Proctor mold. Just basic theory of elasticity, don't need to go through the details. But again, in the field, typically we're using a 300 millimeter diameter plate in a full drop height, and the stress conditions in the field are different. When we're dropping it on the Proctor mold, we've got a confined specimen. It's only 100 or 150 millimeters in diameter, and so the full drop height gives us stress levels in the mold that far exceed what we see in the field, and so that's the reason for going to partial height drops, so that we can interpolate to get the right stress levels for comparing with the field. And in the process of doing this, we developed a whole bunch of refinements to how you do the LWD drops on the Proctor molds, and came up with a bunch of guidelines here that got built into the specification for actually doing the tests. And in the field, again, so this is just basically your standard Boussinesq equation for if it's a subgrade you're testing on. So the standard Boussinesq equation with some wrinkles here that in all of these elasticity equations, you have to have a Poisson's ratio, which we typically have to assume. We're not going to measure that. And then there's always this issue below foundations. What's the stress distribution below foundations? Is it a uniform contact pressure? Is it a parabolic or an inverse parabolic? And it depends on the soil type, typically. And so there's this stress distribution factor A, which we get based on the stress distribution shape here. And then basically we've got the peak load and the peak measured deflection. And we use that all factored in here to back out the field modulus. It gets a little bit more complicated if we're dealing with a layered system. Okay, what I showed there is if I'm testing directly on the subgrade, so I've just got a homogeneous single layer. If I'm testing on the top of my granular base layer, well then the stiffness, since the subgrade is typically within the zone of influence of the load, that the stiffness of that subgrade is going to influence what I measure on the surface. And what I'm measuring is a surface modulus. So if I know the surface modulus and I know the stiffness of the subgrade, I can combine those two to back out what the real stiffness is for this granular base layer. And this is just a technique for doing that. It's a correction factor basically based on the structure of the layered system. And this just shows an example. This was in Indiana. Indiana does a lot of cement stabilized subgrade construction for pavements. So you have a very stiff subgrade, much stiffer than the granular base layer typically. And so this red line is the granular base stiffness we measured in the laboratory from samples taken at these locations. And again, it's pretty constant. We're measuring in the laboratory. Then before placing the granular base, we went in and measured the subgrade stiffness using our LWDs, and that's the purple line here. And I can see I've got a couple of areas here where I had particularly stiff subgrades. Okay, so then what I do is I go and knowing the stiffness of the subgrade and knowing the stiffness of the base layer from the laboratory, I can go and calculate what my target modulus should be for the surface modulus measured at the surface, which blends together the influence of the subgrade and the granular base. And so that's the green here is the target. And then what I've actually measured on the surface in the field is the blue. Okay? And so in this case, I've actually I've lost battery here. Not met my criteria here. I've not met my target at that point, but I have over on that stiff point. So again, so that's just taking structural effects into consideration. So what we were finally after at the end in the field validation is this, a series of plots that look like this, where what I'm plotting, and again, this is very, very small. I think the battery's dead on this. The vertical axis on these plots are the percent compaction that we get from density. Okay, you know, a typical compaction spec would be you have to achieve 95% of standard Proctor compaction in the field. Okay, so that's what we're plotting on the vertical axis, percent compaction. And the horizontal axis is the ratio of the field modulus to the target modulus, the actual measured field modulus to the target modulus we determined in the laboratory. And the blue lines basically are showing values of 1. 100% compaction by density is the horizontal blue line. A modulus ratio equal to 1 for the vertical blue line. And what you're seeing on the right are basically the compaction curves and the stiffness versus moisture versus drop height curves. But what we're looking for is its verification of the process is what we're looking for correlations here. We want to see if this section passed specifications based on density, does it also pass based on stiffness? And that's what we're seeing here. Typically, for these projects, the threshold for percent compaction by density is about 95%. And all of our points for this site are above 95%. And in terms of stiffness ratio, they're all above 1. Okay, and so we've passed both criteria here. And that's what we're looking for. Some more sites. This is one that failed. Okay, and again, you look at the percent compaction by density on the vertical, and all of these points are below 95%, the dashed blue line. And they also have a modulus ratio less than 1. So again, we're getting agreement between density and modulus.
What are the error bars representing?
We do a whole bunch of drops at each location. Typically, for a lot of these sites, what we would do is go right after compaction, and we come back at hour intervals and collect some more data. And so that's what you're seeing there.
The error bars are like the standard deviation.
Yeah, standard deviation, right. And again, so some more down here where we pass both density and stiffness. Again, some more where we pass. And then one down here where we were compacting over a very wet local subgrade, and we failed. We were sort of okay on, well, no, actually we failed on both density, and we're a little bit below a modulus ratio of 1, but we really failed here because of moisture content. We were outside the moisture content tolerances. So again, the point of this was, in the conventional way, if we would have said that this site passed the compaction requirements based on density, would we also say it passed based on stiffness using this technique, these specifications we developed? And the answer is yes, for a limited number of sites. Again, for all the sites we looked at, a lot of them we had to reject because they didn't meet all the requirements of the specification by the time we had refined it. And so we were able to come up with a bunch of recommended target values for these materials. And at the end came up with these 2 proposed specifications. One for how to do the laboratory determination of the target modulus, how you prepare the sample, how you do the testing, et cetera. And then the second one is how you go about doing this in the field. And that includes things like the required testing frequency that you should have for your testing program. And so then the next step is for implementation is for individual agencies to go out and do some local calibration of this. And the argument for this is as follows. When we do density-based compaction control, we don't require that you compact in the field to densities equal to 100% of maximum dry density. Typically, agencies will specify 95%, 93%, whatever. And so the question is why? Why not 100%? Well, it's a question of what you can achieve practically in the field and economically in the field. And this is something that evolved over time through experience. Well, we have to do the same sort of thing for the stiffness ratio. We don't necessarily want to require a stiffness ratio of 1 or greater, okay? In the same way that we don't require density equal to max density or greater. We probably want to set that compaction specification threshold as something a little bit less than 1, again, to be practically achievable in the field. But we don't know what that number is because we don't have a lot of experience doing this kind of testing yet. And so what we had proposed and what we're currently doing in Maryland is going out now for a wider range of test sites and repeating this kind of study, doing nuclear gauge testing and lightweight deflectometer testing to figure out from that set of data what this right specification threshold should be. And again, to build better confidence in the model. But that's a fairly limited exercise. It's not a big project to do that, and we're in the midst of doing it now. So anyway, so that, this worked out well. I think this is going to be a practical, usable technique. And again, even in places like Minnesota, where MnDOT has been doing this for a long time, they've been doing it based just on the deflection of the lightweight deflectometer, which again is not an input to pavement design. What's the input is stiffness, and that's what our approach gives. And so this approach actually allows the designer to confirm design intent. Was the compacted layer, did it achieve the stiffness that was assumed in the pavement design? So you get to close the loop in the design process. So again, a lot of people involved in this, and with that, we've got a little bit of time left for questions. I'll throw it open. Thank you.
So any questions from the audience? Okay, I'll go with
So I just wanted to ask for a little bit more clarification about those plots that I was asking about, and then I have a follow-up question about that.
You want me to back up to those?
Yeah, that would be helpful. And this is sort of coming from, not that one, the ones that I was asking questions about where you have E versus E, and then you have the line that's the equivalent line, and then, yeah. So, okay, wait, can you just stop right there?
Oh.
Yeah, so that the lab, so you had you were comparing two different values of E, not that one, but
that's this one.
Right, so
yes.
you're comparing, and so is it basically laboratory measure?
They're both field measurements, okay? The only difference is the vertical axis is the dynamic plate loading, the lightweight deflectometer with a drop weight. And the horizontal axis is a conventional plate bearing test, which is applied at a monotonic, slower loading rate.
Okay.
Yeah.
And this is just to understand the differences. I didn't quite catch why you did this. Is it because different places have different specifications and you're trying to understand?
This is just an example of the kinds of results. We collected a lot of data at these test pits, some of which fed into the development of the specification, some of it didn't. This is just one example of the kinds of data we got, because this is one of the things that people often take a look at, how the stiffnesses from the dynamic drop weight, compare with what you get from a slower monotonic plate loading test.
Why do people, why are they interested in that? Is it like a dynamic loading from sort of trucks versus just someone, like a bunch of material sitting there?
So there's three things here, I would say. One is that the reason we compare with static plate loading tests is that's an old technology that people are a little bit more familiar with. So we're sort of touching back to technologies that people have some comfort with. But you hit upon a couple of good points. The lightweight deflectometer is intended really to simulate more closely, not exactly, but more closely the kind of dynamic loading you get under moving traffic, which the static plate loading test doesn't do. And there can be significant differences. If I had a very high moisture content subgrade, for example, I would expect to see probably much higher modulus values from the dynamic test because of excess pore water pressures, water being trapped, as opposed to the slower static plate loading test where I get some dissipation going on.
And then you sort of mentioned quickly in passing, and I guess this is maybe a follow-up testing of how you got modulus from a number of things, and one of the things you said was the Poisson ratio, and of course, you said, and so this is going to be a even more naive question, we can't measure Poisson ratio, so we make some assumptions, and so what's sort of like a gradient-dependent assumptions that you make for Poisson ratio, or do you just put
Okay, so again, within the confines of theory of elasticity, it can only be between 0 and 0.5. And typically in soils, we think of if a saturated material, saturated clay, 0.5, no volume change. For unsaturated materials, it's over a narrower range, 0.2 to 0.4, something like that. We can measure it in the laboratory. We can do a triaxial test in the laboratory and measure Poisson's ratio, but we're not going to do it for this because it sort of defeats the whole purpose of our approach. We don't want to do resilient modulus testing in the laboratory.
Right,
And
so I guess my question for that is, do you sort of look, and for this particular test, you're looking at the subgrade, which typically is coarser, and so then you use the following for the Poisson ratio, and then you change the Poisson ratio for a more clay soil when you're dealing with that, and so you sort of adjust it with...
clay
okay.
soil.
Okay.
Now, so you have to, if you don't measure it in the laboratory, you have to assume it, okay? And this is the same, anytime you apply theory of elasticity to soils, you're typically assuming a Poisson's ratio value because we don't go and measure it typically. But one of the things, I should have mentioned that, I should have emphasized this more, that when we're doing this, the requirement is that whatever device you used in the laboratory, you also have to use in the field, okay? Because the devices give different values, okay? And so that cancels out some of those variations. And the same thing with Poisson's ratio. What you assume for interpreting the laboratory data is going to be the same value you assume for interpreting the field deflection data, the field stiffness. And so if it's not the right Poisson's ratio, at least you have some canceling out of that effect since you're using the same value for both tests.
And it enters into the equation in the same functional form?
No, it's not exactly the same because they're different stress distributions. In the Proctor mold, it's a homogeneous uniform stress distribution, and it's not in the field. So there are some differences. So, but you know, again, this is we're looking at we sacrifice some of the theoretical purity here in order to come up with a device and a technique that actually get used, that can be done quickly in the field and economically in the field. So, yeah.
That's a good segue to my question. It looked like your error bars were actually rather large. And having something that's quick and will be used doesn't mean it gives good results. So nowhere in here did I see anything about how many measurements did you need? Did you replication sampling?
Yeah.
To me, my problem with the lightweight deflectometers is, first off, it's really easy to do it wrong. Mm-hmm. And secondly, if I take a measurement, I move over 6 inches, take a measurement, move over 6 inches, take a measurement, I get significant variation.
That's true. That's true.
So it's fast, it's easy, it gets used, but the data's crap.
Yeah, and frankly, you have a lot of the same thing with nuclear density gauges. If I move from one point to another, so I didn't talk about it here, but we addressed that as part of this. I did mention it at the end in terms of the second spec. There's actually a section in there that suggests how you determine testing frequency with the lightweight deflectometer, and it's based upon the variability for the lightweight deflectometer data that we observed in our tests as compared to the variability in the nuclear gauge. See, the nuclear gauge data has not quite as large, but that has significant, the vertical error bars are not insignificant also. And so what we did is we said, okay, you've got a specification that says you have to do X number of nuclear gauge tests per however much material. Okay, so we said, okay, if you have to do that many nuclear gauge tests and they have a certain variability, and I've got lightweight deflectometer that has a different variability, how many of those tests do I need to do to get the same confidence levels? That's basically it. So that's in the spec. Yeah. Yes?
Just a quick follow-up question to Randall's. A quick follow-up question to Randall's question is, it has to do with, my understanding is the first several tests, there's some unsteadiness. And then you get a steady result. So if you take it from right after compaction, as that implies, then there's going to be bigger error bars just because of the compaction isn't perfect at first. So is that maybe included in the error bars? I mean, there must be some, maybe, again, it's like if you go from one set of tests to the other, as long as you do maybe the same standard what do I want to say, procedure. Yeah.
That, I think what you're talking about is the seating issue. And that's part of all of the lightweight deflectometer specs, ours included, that typically what you do is you very carefully smooth out the soil surface and you put this on. And then you do 3 drops just to seat the plate, and you don't take any measurements then. And then it's the subsequent 3 drops that you take. And those at that point, those tend to be pretty uniform.
Okay, that's my question without using the word seating. But
okay.
Yes, yes, so thank you.
Yeah.
Any more questions?
There are other things involved with the seeding also, depending on the soil. Sometimes you put down a very thin layer of sand to make sure you have uniform contact, and there are tricks involved in getting good data out of this.
So I have a question. I'm farther from this area than the previous two questions, maybe than this question next to me. You mentioned that there was moisture content in one test that failed that was outside of the range acceptable for these types of deflectometer tests. Now, this is in the environment. You have different moistures. Why would one be outside of the range?
It's the moisture content at the time of compaction that we're looking at. You're right. I mean, you place the material and it's exposed to the environment, and the moisture content is going to change. The compaction moisture content is usually not the equilibrium moisture content for the material, the natural moisture content. And what you typically find is that for pavement applications now, for granular base layer, coarse layers, typically they dry out, that the compaction moisture content drops after they're in the environment. And for fine-grained subgrades, you actually have the opposite, that they tend to get a little more moist. The moisture content increases over the optimum moisture content. So what we're really looking at, and so for compaction purposes, we're not caring what the natural moisture contents are, because we're trying to control the moisture content at which we place these materials. Even for a subgrade, we may excavate off the top part of subgrade and then replace it. But what we're trying to do is to compact near the optimum moisture content for two reasons. One is that we know that's our most effective use of compaction energy. From our laboratory testing, we've determined that that's the moisture content that for a given amount of compaction energy, we get the most density. So we want to be around that sweet spot in the field for testing, for compaction. And the second thing is that for certain types of soils, for clays in particular, if you compact dry of optimum versus wet of optimum, you get different microstructures for the material, and it behaves differently. If you compact wet of optimum, it tends to be a more plastic material with lower permeability. If you compact dry of optimum, you get a flocculated structure, which tends to be a little bit stiffer and higher permeability. So there are those considerations.
So all these answers relate to the tests.
Mm-hmm.
But how about reality? In reality, you're going to have all kinds of moisture contents, and I'm thinking you probably want to take the worst condition to test the compaction of your soil, wouldn't you?
Well, not for pavement design, for pavement performance. That it's true that the moisture content changes, and even in the old empirical AASHTO design framework from 1993, you didn't use the most conservative assumption for stiffness. What you were supposed to do is to come up with some sort of seasonally adjusted average modulus value that reflected the fact that in the summertime it was dry, in the spring it was wet, and so on. It was a complicated process that people frankly didn't use, and so they kind of pick a number. In the newer design procedures, the mechanistic empirical pavement design procedure, part of the mechanistic analysis is a module that actually tries to predict moisture and temperature in the pavement versus depth and over time. Now, it's not perfect. It's imperfect. There's a lot of things that are wrong with it, but that's where we're going, to have a more mechanistic way of seeing how moisture content fluctuates, temperature fluctuates, and what effect that's going to have on the material properties, on stiffness in particular.
Okay. Yeah. So there are corrections for that then?
Yeah, yeah.
Okay, thank you.
Last question.
Thank you. Did I understand correctly that the point is that you are below at the right place relative to the blue lines, right?
In this particular case, on the upper set of graphs, no, that failed because it's below.
No, I understand, but
yeah.
the goal is to make sure where they. So isn't then the error bars included in? So if the error bar would pass the blue line, would it fail?
I mean, if some of the error bars extended across the blue line?
Yeah.
Well, no, I mean, you would go to a percent within limits kind of specification where you recognize that because of variability, not every single data point is going to pass your requirement, but you're going to require a certain percentage of the data points to satisfy your requirement.
And how many of these experiments did you do to determine those error bars?
It varied from site to site. On this one, we had I forget how long this site is, but for this New York embankment, there were 2 lifts, so I think we tested on each lift. Typically, we'd test every 10 feet, however many we could get done in an hour, and then we came back and did 2 more rounds of testing after that. So there may be as many as 30 or 40 data points.
So quite a few, yeah.
Okay, so Professor Schwartz will be available upstairs to talk to and answer other questions, but
Sure.
we have to end now. So let's thank Professor Charles
Thank
Schwartz
you.
for a very good presentation.
Take exception.